I'm Sebastian. I'm with Twitter. I'm a senior video engineer for Twitter and working here in London with the Magic Pony team. Our team is working on video compression and machine learning, and I'm responsible for video compression technologies within the whole of Twitter. If you're not aware why I'm standing here in front of you and talking about video at Twitter, that's why I'm going to have the first bullet point to discuss what video is at Twitter. Secondly, I'm going to discuss with you what we're doing in terms of visual quality. And I will highlight first what are existing visual quality metrics, and secondly, I will discuss a method which we have developed to improve existing systems. But first of all, video at Twitter. You are probably aware Twitter is a service where you can generate messages and text messages of 288 characters, but you can also embed images, videos, and GIFs. Also, advertisers, they can send video, but what is actually more important these days are our live product offerings. One of them, for example, is Twitter Live, where you can see at the left-hand side, where The Verge has, for example, covered CES 2018. Also very important to us is Periscope, which is a live streaming social media application, which is part of Twitter and as 14th of December 2016 integrated in the Twitter app. And this happens to be the date that Amazon Prime went live to 200 countries, I learned today. So it must be a great day for video compression engineers around the world. But not only we are bringing video in products, we are also trying to improve video. We are trying to improve the product experience towards our end users in general. And we also try to research and do research, perform research, and give back to the communities. So that's why in 2016, Magic Pony has been acquired to make sure that we can do research in machine learning and video compression areas and improve the state of the art there. We have recently open sourced a Viral library, which is a lightweight library to do video processing and video encoding, which allows you to run on a large-scale video encoding infrastructures. My colleagues from Periscope have recently written a blog post on low-delay HLS, which is a form of transmitting HTTP adaptive live streaming video with lower delays. Just to make sure that the conversation which is happening on Periscope can be much faster. So if you record something and it's in a chunk of 3 seconds, you don't have to wait until the full 3 seconds have been available. So you can get everything much faster. And more recently, we have released opened two data sets for 2 conferences, one CVPR and one ICME, where we are co-organizing together with Google for CVPR and together with Twitch for ICME grand challenges. So in this way, we as Twitter try to bring products to our users, but also try to give back to the people and try to move forward. And one very important way for us is to understand how our users are watching video, and generally our users are mobile device users. So this might be different for YouTube, this might be different for Amazon, this is probably different also for Sky, but for our users are generally on mobile devices, and they're not always on corporate Wi-Fi networks where they got 10 megabits per second. They might be out in London, they might be in the city center where they've got a crowded mobile network. They might be in remotely areas where there's almost no coverage, and still we want to bring them video. So it's important for us that we can do so. To do that, we have a system to adapt the bitrate of the video we're delivering. So if you don't have high bitrate available on your network, you're going to get a lower quality video. If you do have high quality network, then you're going to get high quality video. But nevertheless, it's important for us that in all these situations, we know that our users are getting the best quality. And how do you know that somebody has the best visual quality? You have to measure that. So let us look for a brief second in how to measure visual quality and how that's done both in academia and industry. And in general, there are 2 domains here. One is to do this objectively. You only use mathematics, simple operations which you can do easily at scale. And another one is you make people watch video and you just ask them, how does the video look like? So for the objective metrics, which are based on mathematical operations, some of the engineers in the room might remember the PSNR peak signal to noise ratio from the engineering courses. We've got something similar for video where we are doing a pixel-based comparison. And if both images are looking very similar, if the quality is very high, then you're going to get a very high PSNR. Unfortunately, sometimes images shift to the left, for example, due to some pre-processing or post-processing step, and PSNR will fail there. So another metric called Structural Similarity Index, SSIM, is compensating for this. However, if you look over time, there might be some blurring effects because of motion in the image and stuff like that. So that's not compensating for that. The VQM, video quality metric, is designed for that. And still, if you've got different types of video content, they might look all the same, but you might get different outcomes out of these mathematical operations. Recently, Netflix announced the VMAF, or Visual Multi-Method Assessment Fusion, where basically they have a machine learning system which is analyzing the video, and deep inside the machine learning system they have a lot of different metrics which are being calculated, and the machine learning is generating one single value out of this. So few of the problems with this is that none of these metrics really understand the scene. It might be low motion documentary, or it might be a very fast motion sport game, and how you perceive that scene might be different based on that type of content. Also, the results are not really, the results are content dependent. So for even in the same type of content, one specific scene might end up with a high value, why it's not perceived that high, for example. So there is like a large variability in the correlation between the objective and the subjective quality metrics. And lastly, and that is for us as Twitter, a very pity, none of these metrics are actually designed for mobile phones, because all these systems are generally designed for TVs in a living room environment. So mobile phones have a different type of different type of characteristics. So if we look now in the subjective quality metrics, what is available and what's easy to do? One of them is mean opinion score, and this is like my favorite because it's the easiest one, but it's also not really the best one. You just have your videos, you encode them at your different settings you would like to test them. And you randomly pick one and you ask a rater to give a value from 1 to 5. How do you like this video? So how do you like the quality of this image? 1 is very poor and 5 is very good. Yeah, it kind of depends, right? It depends on what you expect to be poor and good. So then you need to train people, but once you start to train people, they're starting to look into detail because they become aware of where to look at. So it's not really the common user anymore. So we used this very easy method, and we did an experiment. This is the outcome of an experiment where we had 2 types of video qualities. We had 32 samples, we encoded them at a low quality, and the same video samples, the same content, we encoded them at a medium quality. And this is the outcome. The height of the bar represents the average perceived quality by this group of humans. The black line in this graph represents the confidence interval. So if you look into statistics, that's pretty important, and large confidence interval is not something you like. So we can see already for the low quality, the one on the left, there is a pretty large confidence interval. Now we did the same test with different settings, the same content, and we reused the medium quality encoded videos. And we did a test with high quality encoded videos. And what we can see right now, it's very nice. The high quality encoded videos are perceived as a higher quality. However, those medium quality encoded videos, they are now perceived at a lower quality than in our initial test. So which test do we need to believe? And also the confidence intervals are not really overlapping. So if I go to my manager and say, like, look, I've got this great new idea to encode video and it's going to look better, and they ask me how much, and I have to say, like, enough or maybe better, they're not going to really believe me and ship this feature, right? So they're very inaccurate results. They're inconsistent between tests. They also require a lot of people to watch this, because if you've got a couple of people, the results might be all over the place. And also, it's very hard to interpret a value. What does 2 mean? What does 4 mean? Is it double the amount of quality? So it's very hard to also communicate that in the chain of hierarchy. So another method that's been used a lot is double stimulus models. Basically, it's the same as the mean opinion score, but you're not only showing the sample you have encoded, you also show the original or a very high quality. So you tell people, this is supposed to look like a 5. So the one at the top is supposed to look like a 5. And please give me now a rating between 1 and 5, what you believe the quality of the second sample should be. Now, I'm showing you images, obviously, but we do this with videos, so you can see artifacts moving all over the place. So if you do that, you pick another random sample, and eventually somewhere in your test, and I hope you saw this very brief difference in quality, because it's very hard otherwise to show on a projector. So somewhere in the test, you take the other sample, which is now shown at the bottom, and you hope that people, given the reference, then now give a different value compared to the one they give in the beginning. And because they've got this reference, they now are more aware of what a 5 should look like compared to what a 1 or a 2 should look like. So we did a test again with this. And these are the results. Again, the first 2 left bars are the results of the first test, and the 2 right bars are the results of a second test. And the 2 bars in the middle represent the same samples. And very nice, we can see now between the tests, the results are more comparable for the same settings. However, we see also that for the low quality, we still have a huge confidence interval, so we still don't know whether we should think it's 3.0 or it's more like a 2.8. So that's very hard. So there's a higher consistency between the tests, but still not good enough to still inaccurate results. Still, we don't have a linear interpretation of those values. So still, I can't really use this and go to my manager like, look, I can improve video. Still not worth it. So a third type, and then I'm going to stop boring you with exists, and then I'm going to discuss with what we did, is a paired comparison, where basically you take your reference sample, or you take the sample people want to rate, and you've got a huge amount of reference samples encoded at different qualities. They might or might not correspond to the encoding settings you use for your test, but they now know what a 1 should look like, what a 5 should look like. You randomly pick your sample, you randomly pick one of those references, and over time you pick the same sample again, and you pick a different reference. Now, this is very, very great because you can pinpoint very accurately where that quality should be, or where that quality is actually perceived in space, if you've got enough samples in your reference set. But if you do that, you also have got a very large test. So the results will be more accurate because you can pinpoint it, and you need less raters because in general the results will be more consistent between the raters. So your confidence interval is going to be smaller. But it's very time consuming, and if you do a test like this for an hour, you're going to start making mistakes. Either you don't see the difference anymore, or you're going to start giving wrong answers because you're just tired. So that's also not something we can do at a large scale. So I discussed this with my team, and as I mentioned, I'm working for the Magic Pony team where we've got a lot of people involved in machine learning. They say like, we can solve this. Machine learning can solve everything these days. But these guys are really smart. They say like, we can make you something that looks like the paired comparison, but you only have to look once to every sample, which is great, right? So we've got a large set of videos. So that should correspond with all the types of video we're going to see in our system. You only show each sample once, so we reduce the test size. And then we're going to pair a sample with a reference. It's kind of what we saw with the paired comparison. But we're going to take for a different sample in the same set of settings, we're going to take a different reference based on the results we got from the past. So we adaptively are going to select a reference, hence the name adaptive paired comparison. So in our experiments, we're using 32 samples, and we've encoded the same 32 samples in 50 different ways. So we've got a reference scale of 50 values. So you can understand that having now 32 times 50 samples is a little bit much to make all the paired comparisons. But we now can do that in just 32 samples for every experiment setting we would like to evaluate. And the scale goes from very, very bad, something I hope we will never show to people, and I hope people in the room will never produce to show to their customers. And it goes to very, very good. Something we as experts have very hard seeing the differences in different reference on a mobile device. So this is your corpus of 32 samples. And we randomly pick one. So let's assume these are the 3 first samples we're gonna pick for this test. And then we've got our reference scale. It goes from really low to really high. And we randomly pick one for the first sequence with the kit. Our particle filtering algorithm is basically the backbone of the paired comparison algorithm. It's a sequential Monte Carlo system where you're going to update the probabilities. And this basically is going to give us the reference. And we're going to tell them afterwards what has been better, either the reference or the sample that has been shown to the user. And if he knows that, he can update the probabilities, or where is the most, where the sample, or what's the quality of the sample most likely, and then he can give us a new reference to make sure that it converges to that point. So if we are going to do this experiment and we're going to do that with multiple quality settings, we obviously need to keep track of all the ratings for every set of for every pair of our settings. So in the case where we do low and medium quality, we've got one set of probabilities for the low quality, we've got another set of probabilities for the medium quality, and based on from which set you're going to randomly select a video, we're going to take another part in the reference. So this is very promising, but I'm not going to show you the results yet. How are we going to do this in practice? So at the left-hand side, we've got the storage. We've got a large amount of video, and these are Creative Commons licensed videos which we can find online. For example, Blender Foundation has great videos. Netflix recently open sourced a couple of videos, and we encoding in a large amount of settings, and we store them at the server. Then we're going to look into what do we actually want to experiment with. Let's tweak some parameters, and we're going to encode those 32 samples with different parameters. We store them, we gather the data, we give that to a task service, which basically just tells a device where the stored samples are for both reference and the samples in the experiment. The device communicates with the task service, gets all the data, and now it downloads those videos locally on the device before it plays back. Because we care about the visual quality, and if things go wrong, if your network bandwidth drops, obviously you're going to see a lower quality, and I understand your experience will be not really optimal, but I only care about what's the ideal setting I can produce for the video to make sure that the quality you're going to see is optimal for the settings, for the environment you're working in, you're active in. So the mobile device is an in-house device. It's owned by Twitter. We give it to a set of curators whose job is to, amongst this, to label a lot of things. So they switch off the mobile device, they connect with the server, they see there is a task, they start rating the task, and for every mobile device we store the results on the results service. That particle filtering algorithm, which is basically the backbone of our adaptive pair comparison method, runs on the mobile device. And when it's done, when we aggregate all the results, we rerun the particle filtering algorithm to finally come up with a single rating. So how do these ratings look like? This is an example, and on the x-axis we see the quality of the reference videos, which goes from 0 to 50. And then every dot represents the answer of a paired of the question after we showed a pair of both the reference and a sample. And the question is very simple: does the reference look better than the sample? And the size of the dot indicates the amount of times that specific reference has been taken. So if we plot all those on the graph where the y-axis represents the proportion of the videos that have been better in terms of the reference compared to the sample, then we can see that if we plot a sigmoid curve over those, that in the middle of that sigmoid, that's basically the spot where you would not notice the difference anymore. And if you're not noticing the difference anymore, you're starting to guess. And if you're starting to guess, one time you're right and one time you're wrong. It's kind of as simple as that. So if we know at what quality level you're starting to guess, we know that that's the quality level for our set of videos, and we know that that specific level is the level where you are serving, in general, all our videos at. So this is now the outcome of an experiment we did, and again, we did the experiment twice. First, low and medium quality, and then again, medium quality and high quality. And what we can see right now is that between those results, the level of the perceived quality level of the medium quality is identical, or very much identical. The confidence intervals are overlapping, so we're pretty sure it's going to be there. We also see that in general for the other experiments, the confidence intervals are pretty low. Furthermore, the scale of 0 to 50 is not made by random. We made sure that every step from 0 to 1, the subjective quality difference is identical to the step from 24 to 25. It's identical to the step from 44 to 45. So we now know if we say it goes from 25 to 50, we know the exact quality increase we are giving on a general amount of video to all of our users. So if we compare this, then on the left-hand side we see the results of the mean opinion score, where it's very hard to replicate experiments and it's very hard to over time reuse data from experiments. The double stimulus mod kind of improves that, but still not good enough. And on the right-hand side, our proposed adaptive paired comparison, which now allows me to do an experiment, go back to my managers and say, this is a proof that setting A is better than setting B, so we should try now an experiment on our devices in our platform using the better setting, because we're going to have an increase of X. So by doing so, let me give you now a summary. By doing so, Twitter offers a lot of video products, both live and non-live video products. But for all of them, the experience of the user is very important. So we would like to improve that in all conditions, for all devices, for all network conditions, and all the use cases you can think of. Before we can improve your experience, we need to know what your experience is in terms of visual quality. So the existing visual quality systems, both for objective and subjective, were not good enough for us. So we designed the adaptive paired comparison one, where we can now easily replicate results. We can easily interpret results, and we've got consistent and accurate results both within a test and between multiple tests. So I would like to thank the Magic Pony team, which we got a great deal of the work done, which was discussed here. And specifically, I would like to thank Catherine Storrs, who was a postdoctoral visiting researcher who provided a lot of the mathematical background for this, and who assisted a lot with all the technical details, which I described in here. I was Sebastian. I'm with Twitter, and if you have any questions, you can either tweet me or you can ask them right now. Thank you very much.